Hello, I'm Saumya Sadanand from IMDEA Materials, and I'm completing my PhD in iron-based metallic glasses produced by LPBF or laser powder bed fusion. So my project deals with a specific soft magnetic component that is used inside electric motors, which is the rotor, that is the rotating component inside an electric motor. So the project that I used to work in, is AM to Soft Mag. That it is funded by the European Union through a Horizon Europe Pathfinder Open 2021. I entered into a completely new territory with this project because I was dealing with a composition that had never been tried out for laser powder bed fusion testing before. So then we became the first people to work on it and publish a proper processing window for these materials. So I think that was a big achievement there. And then eventually we also produced another paper. This is specifically focused on crystallization mechanisms in this particularly very popular composition that is fine met. So fine met as a composition has already been popular in the magnetic literature. That's what we knew from our colleagues in Italy. But then we started understanding the challenges specifically based on the processing and how it was not going to be as perfect for application into industrial applications. And then we started digging deeper through it through microstructural studies, which is the second paper. We tried to understand why it has not been explored that widely, because it has certain limitations in terms of microstructural features. So my work here has been majorly to produce the iron-based metallic glasses in their fully amorphous state. In the first part of my PhD, we were not quite there. We were like 50% amorphous. And from the second part of my PhD, in the project, we came up with a new composition that had a higher glass forming ability than the previously fine met composition, with which we were actually able to produce 100% amorphous materials. And that was, I would say, the biggest breakthrough of the project. And once we had them in their fully amorphous state, we were then able to play around with a little bit of geometrical intricacy that we could achieve. During these 3.5 years, I got very comfortable with microstructural characterization, powder characterization, and understanding how powder flow characteristics can or cannot affect your eventual printing in the LPBF system, and eventually testing all the printed parts via mechanical testing, structural analysis, and then making reports, presenting it to different people in the consortium, and also presenting it in international position. I think all of these are very valuable skills that are directly transferable into an industrial job or whatever you like after your PhD. In my experience, the biggest challenge and the biggest opportunity to learn lies in the fact how efficiently you can print in the LPBF system that we have, because it takes up to a full day or even longer to get your print done from the start of the print to the end of the print, and cleaning before and after. So that can take up a very long time, but you also need to be a trained user to do all of those thousands of steps equally efficiently. The past 3.5 years have honestly flown really fast. I think I learned a lot as a professional and also on the personal front, because I think most of us join here in early to mid 20s, and by the time we finish it, we also become new people when we leave, almost ready to conquer the industrial world or a postdoc or an academic field. On both fronts, it's been extremely fruitful. If I was starting my PhD right now, or if I were to suggest someone that is going to, I would say record everything that you do in the first year, from the first year itself, because you don't know at what point a trivial result can become really valuable when you're publishing something.